Alright, welcome to this explainer. Today we're diving headfirst into literally the ultimate cosmic crime scene to investigate the absolute greatest mystery in astrophysics, how our universe was actually made. We're going to be looking at the initial clues, the prime suspects, and a massive, completely groundbreaking paradigm shift that is happening right now in modern physics. So let's jump right in. We really have to start by asking a deceptively simple question. Why does our universe look the way it does? I mean, when we look out into the cosmos, we see a universe that is incredibly smooth, phenomenally flat, and just exquisitely structured. So why isn't it a chaotic, lumpy, irregular mess? Because mathematically speaking, that kind of perfect uniformity, it's highly, highly suspicious. To put this into perspective, our current observable reality spans a staggering 93 billion light-years in diameter. And look, as brilliant as the classic hot Big Bang model is, and it is brilliant, it alone simply cannot explain the bizarre clues scattered across this unimaginably vast space. It does a great job telling us how the universe evolved after that first fraction of a second, but it completely breaks down when trying to explain the initial setup of those 93 billion light-years.
So, Chapter 1, the crime scene, fixing the Big Bang.
To really understand why scientists were forced to hunt for a completely new theory, we have to look at what was broken. Back in the 1970s, physicists noticed three really deep flaws in the standard model. First up, the horizon problem. Basically, distant cosmic horizons have the exact same temperature, even though light literally hasn't had enough time to travel between them to exchange heat. Second, the flatness problem. The density of space is suspiciously balanced to 1 part in 10 to the 60th power. No way that happens by chance. And third, the magnetic monopole problem. Grand unified theories strongly predicted the universe should be cluttered with these massively heavy relic particles, yet we haven't found a single one.
And this brilliantly illustrates the real issue. Reality completely contradicts the early predictions of the Big Bang. Instead of the predicted curved space and chaos, we observe perfectly flat space, a shockingly uniform 2.725 Kelvin background, and absolutely zero monopoles. This stark contrast means something else. Some radical event had to occur in the universe's very first fraction of a second to fix the math and set the stage for everything we see today.
Which brings us to Chapter 2, the prime suspect, the inflation engine. Enter cosmic inflation, a theory proposed by physicist Alan Guth in 1981. We are looking at an absurdly brief and incredibly violent window here. Somewhere around 10 to the negative 36 seconds after the Big Bang, the universe essentially kicked into hyperdrive, and by 10 to the negative 32 seconds, the whole event was over. So what fueled this hyperdrive? Well, for 40 years, our prime suspect has been the inflaton field. It's a hypothetical quantum scalar field. Imagine this invisible potential energy landscape where this field is slowly rolling down a hill. While it's perched up high, its energy acts as this immense repulsive force embedded in space itself, driving an explosive, exponential expansion. To truly comprehend the sheer scale of what this inflaton field supposedly did, just look at this number, 10 to the 26th power. In less than a blink of an eye, a patch of space smaller than a single proton expanded by a factor of at least 10 to the 26th. It basically ironed out the cosmos, stretching it incredibly flat and diluting all those unwanted magnetic monopoles away into nothingness. It's literally like taking a tiny, completely wrinkled balloon and inflating it to the size of the Earth. All those local wrinkles just vanish. Chapter 3, the blueprint, quantum seeds of reality.
But here's the absolutely crucial point. If inflation flattened everything out perfectly, how did we end up with galaxies and stars and us? A perfectly smooth universe would just be a boring, dead void. The answer is an amazing trick of scale shifting. You see, even in an empty vacuum, microscopic quantum jitters are constantly popping in and out of existence. During inflation, space expanded faster than the speed of light, taking these incredibly tiny quantum fluctuations and stretching them to macroscopic sizes before they could vanish. They literally froze into the fabric of space as classical density perturbations. And those frozen ripples? They became the gravitational seeds that would eventually pull matter together to form the galaxies we live in today.
What's truly mind-blowing is that this isn't just some wild theoretical guess. We can literally see these frozen seeds today. They're imprinted as tiny temperature variations in the cosmic microwave background. Inflation makes very specific mathematical predictions about the spectrum of these density fluctuations. And recent observatory data? It gives us a spectral index of 0.9682, which exquisitely matches inflation's exact predictions. After inflation finished its exponential stretching, it kind of graciously bowed out. The inflaton field dumped all of its stored energy into standard particles through a three-step process called reheating. Going from explosive parametric resonance to energy transfer, it thermalized the whole universe into a hot, dense plasma. And actually, this reheating process is what genuinely ignited the hot Big Bang phase of our universe's history.
Moving on to Chapter 4, Unintended Consequences, Evidence, and the Multiverse.
Now, as observatories gathered evidence confirming inflation, theorists formulating the different models realized they had a massive, unintended philosophical headache on their hands. Old inflation failed to exit gracefully, but looking at models like Andre Lin's chaotic inflation, physicists realized something terrifying. Quantum fluctuations would actually prevent the inflaton field from ever truly stopping everywhere. Sure, our little pocket of space stopped inflating, but the space between pockets, it would just keep expanding forever.
And this leads us directly to the terrifying wonder of eternal inflation. It suggests that our universe isn't everything there is. In fact, it's just one tiny bubble in an infinite, self-reproducing, ever-expanding cosmic fractal. And what's really wild is that every single one of these infinite bubble universes might operate under totally different laws of physics. Chapter 5: Cracks in the Theory, Controversies and Critics. Naturally, this whole infinite multiverse concept brought the scientific community to an absolute boiling point, turning theoretical physics into some intense human drama. Critics, including Paul Steinhardt, who, by the way, was actually one of inflation's original founding architects, argued that a theory predicting an infinite multiverse where literally everything happens essentially predicts nothing at all. They claimed inflation had become effectively untestable and therefore unscientific. Well, as you can imagine, this sparked a fierce defense from 33 leading physicists who insisted that inflation absolutely remains rigorously testable.
Driven by these fine-tuning concerns, and honestly the failure to detect primordial gravitational waves so far, critics started formulating some incredibly bold alternatives. We've got bouncing cosmologies with no singularity, Roger Penrose's conformal cyclic cosmology proposing infinite eons of universes, and even string theory constraints suggesting the mathematical conditions required for the inflaton field might actually be impossible.
Chapter 6: The 2025 Paradigm Shift, Rewriting the Cosmic Rules. Okay, get ready for the plot twist. Cutting-edge research from 2025 implies the critics might actually be right, and we may have been hunting a ghost this whole time. A groundbreaking new model removes the speculative inflaton field entirely. Think about it. For 40 years, we relied on a hypothetical field we couldn't even prove existed. But this 2025 paradigm shift proves that the known turbulent quantum foam of spacetime could generate primordial gravitational waves, and those ripples alone could drive the exact same exponential expansion. It's an absolute game changer because it achieves the same result using known physics rather than inventing totally new hypothetical fields. So, where does that leave us? We are standing on the absolute precipice of a new era of understanding. Next-generation observatories, like the upcoming LightBird satellite, are launching specifically to scan the skies for the precise fingerprints, that B-mode polarization, that these gravitational ripples would have left behind in the cosmic microwave background. We are finally going to get the hard data needed to test these mind-bending theories. So at the end of the day, whether the expansion was driven by a magical inflaton field or the raw turbulence of quantum foam, we're left staring at the ultimate question. Is our universe a solitary masterpiece born from an isolated quantum ripple? Or are we just a single droplet in an infinite, eternally expanding multiverse? The search for that answer is happening right now, and the clues are literally written across the stars. Thanks so much for joining me on this explainer. Keep looking up, and I'll catch you next time.